Everyone knows what a magnet is. It's a piece of material surrounded by a magnetic field that can, for example, attract iron. And the origin of that phenomenon is order. So each atom is a little magnet, and when they all line up in the same direction, then you get the magnetic field. There are many other types of ferroic order in nature, however. For example, there are materials where each atomic unit is like a little battery, and if all these little atomic batteries line up, you get something like a ferromagnet, but now it's surrounded by an electric field and called a ferroelectric. And all these patterns, ordered patterns, they can generate very beautiful effects. It gets particularly interesting if magnetic and electric order come together in one material. That's called a multiferroic, and since the magnetic and the electric order then talk to each other, this can be the source of a new type of microelectronics. In order to visualize these types of ferroic order, we use very weak optical processes, so we need a very strong light source. And the strongest light source that we have is the laser. So if you, for example, look at this laser, it's red. Then on the paper, it also generates a little bit of light at a different wavelength, blue. And it's this new frequency component that tells us something about these internal types of order that the material has. The Stern-Gerlach-Medal is awarded for this idea. It's a great honor, but of course the entire group is awarded because they do all the work. We are a very international team because as a member of a federal university, I find it very important to show how much you can gain if people from a very diverse cultural background work together in peace. What brought me to do this kind of work? Well, I grew up in the age of planetary space missions. That brought me to physics. I really like photography. That brought me to optics, and I absolutely adore cinema. For me, movies are a window to the world, and that's exactly why our group is so international.
Ladies and gentlemen, it is my pleasure to introduce the speaker for the next half an hour. My name is Burkhard Hillebrands from the University in Kaiserslautern, and the speaker is Manfred Fiebig, and let me just introduce him to him. He's born in Iserlohn and stayed in that area for quite some time, works especially known for ferroic with nonlinear optics. We will hear a lot about it today. He went to Japan after his doctorate in Dortmund. He was a junior research leader in Dortmund, and later he moved as a Heisenberg Fellow to the Max Born Institute in Berlin. He was shortly professor of experimental solid-state physics at the University in Bonn. Oh, shortly means 2006, 2011, so it was 5 to 6 years. And since 2011, he is a professor of multifunctional ferroic materials at the ETH Zürich in the Department of Material Science. He's also very helpful for us in the magnetism community, since he is the chair of the advisory board of the AG Magnetismus, and that is a DPG-Magnetism working group. He has won quite a number of awards. To name are 2006, the Walter Schottky Award, and then 2016 he has won an ERC Advanced Grant, and last year the APS Frank Isaacson Prize for Optical Effects in Solids. He's fellow of the American Physical Society and also of the Academy of Sciences and Literature in Mainz. And now, most important is this year he receives the Stern-Gerlach-Medal. And actually he hasn't received it yet, but he will still receive it today, namely during the Festsitzung, which will just follow. Here's a talk. So this is the prize talk. And let me give you an introduction to his presentation, and the introduction is nothing else than just a citation for the award. The citation reads, he received the award, or he will receive the award to be more precise, for his application of nonlinear and time-resolved laser spectroscopy, especially frequency doubling, to the elucidation of ferromagnetic order, domain structure in solids, and in particular multiferroic systems with simultaneous electric and magnetic order. Manfred, I'm very much looking now forward to your presentation. So please.
Thank you very much, Burkhard. Yeah, thank you very much. Actually, I already received it last week at the Matter and Cosmos meeting, so it's my second DPG week, which is a weird experience. But nice, very nice. So I still can't believe that I'm standing here talking to you. So I would like to begin this talk with some personal acknowledgements. So I'm very much indebted to Professor Dietmar Fröhlich at the University of University of Dortmund, who introduced me to laser spectroscopy. Then a very dear friend, Roman Viktor Pisarev from the Yoffie Institute in St. Petersburg. He brought me into magnetism, so he's the reason why I'm a spin doctor. Then a couple of colleagues over the years who became friends, Burkhard Hillebrands, but also Nicolas Pauldin, Dennis Meyer, and Hans Kroha. Then, of course, I'm very much very thankful to the German Physical Society for awarding me this medal, for ETH Zürich for providing the infrastructure and much more to do my research, and personally to Gertrud because she moved along with me through all of this. I also would like to acknowledge my group, a very diverse group, and by now with a very large diversity of experimental and even somewhat theoretical tools. So they do the work. Without them, I would be nothing. And as you see, it's a large bunch of people. It's absolutely enjoyable each morning to come to the lab and meet all of them. So then let's start. I would like to give two introductions on ferroic materials and nonlinear optics, and then give a couple of examples that go a little bit into the degrees of freedom of these optical experiments. So first, ferroic materials, and here you really have a very simplistic view of what a magnet is, more precisely a ferromagnet. You have this spontaneous arrangement of magnetic moments that generates an external magnetic field. And this magnetization that you get in response, that can be switched by an external magnetic field, and then you can drive a ferromagnet through this well-known ferromagnetic hysteresis. And this is by far not the only type of spontaneous order that nature offers us. So you can basically do the same thing on the electric side. So you replace the magnetic dipoles by electric dipoles. They can also, under certain conditions, arrange themselves spontaneously, and then they would be surrounded by an electric field. You would have a hysteresis where you drive an electric polarization with an electric field. So here this is called ferroelectricity, and ferro here does not indicate the involvement of iron. It just means it's this kind of spontaneous long-range order that is indicated. Also, this looks very similar, and in terms of the definition of what a ferroic is, these two phenomena are very similar. But of course, it doesn't mean that they have the same macroscopic background. That is in fact vastly different, but the definition of a ferroic doesn't care about microscopy. So if you say ferromagnetism, that's something with exchange coupling. That's not correct. You can build a ferromagnet also from magnetic dipole interactions. And that has been reported actually. So you need to stay macroscopic. And then talking about what is ferroic. So we know it for 2,500 years that there are ferromagnets around. Nevertheless, and you would expect so no later than the 18th century, it was all written down. But in fact, the very first work to develop an overarching concept for what is ferroic order, that's just from 1970. And that was only based on symmetry arguments, so even only covering a small part of that. And if you look at the books that really define ferroic as a materials concept, only one, 2000. That's it. So that means that's, first of all, very surprising. And second, it means that there are lots of little discrepancies, controversial discussions, and so on, what actually is a ferroic state. Okay, so what is it? On the example of a ferromagnet, so a ferroic type of order, it needs to break, it needs to reduce the point group symmetry of a material. In the case of ferromagnetism, you lose the time reversal symmetry. If you imagine a magnetization created by a circular current, classically, time reversal changes its direction. Therefore, time reversal is not a symmetry operation. It's lost when a material orders ferromagnetically. You need to have some spontaneous property that emerges. In the case of the ferromagnetic state, the magnetization. You need to have different regions in a material where this spontaneous property has different orientations. Those are the ferromagnetic domains. You need to have switchability in a conjugate field. That is this hysteresis that represents this property. And there needs to be some susceptibility that diverges at the ordering temperature. When a ferromagnet is just about to order, you need a tiny magnetic field in order to really make it create a magnetization. That's this divergence here. And all ferroic types of order need to fulfill these properties, here written down for ferromagnets, but it should also apply to elastic, electric, and so on phenomena. Okay, then we can also go a little bit one step further. We could ask, why not having two types of ferroic order in one material? That brings us to multiferroics. So a material can at the same time have ferromagnetism and ferroelectricity. That is being discussed a lot recently because of these cross-coupling interactions. So you can imagine an electric field tuning through a magnetic hysteresis. That is hugely interesting because imagine you would manipulate magnetization with a voltage pulse rather than with an electric current. You would save lots of energy. No currents flowing, just a voltage pulse. That's why these materials are so much discussed. Okay, and that also is reflected by the publication activity. That's not our publication activity, that's the community. Good, and then nonlinear optics, why would we need that? So we learned from the definition of a ferroic, there are domains. Okay, regions, you would like to see them, so you need spatial resolution, and humans are eye animals, so you would think about optical techniques. Then we have symmetry breaking, ferroic order break symmetry. So then we make the step from optics to nonlinear optics, because nonlinear optics is very symmetry sensitive. That you can see here. So here is what nonlinear optics, well, how you can imagine it. So you have a polarization proportional to an electric field. You can have higher order contributions like P coupling to E square. If you write that down, you find that with electromagnetic fields, 2 photons absorbed simultaneously, one going out, then necessarily at 2 omega. So this is a process that doubles the frequency of a light wave. It's also called second harmonic generation. That is a process that is only allowed, at least in the leading order, in non-centrosymmetric materials, and there you have your symmetry sensitivity. So if we now look at ferroelectric order, so we have a material that is at first has no spontaneous polarization, then it devolves the spontaneous polarization. Inversion symmetry is lost. So immediately you would expect that some second harmonic signal comes up because now it's allowed. Background free even. The same you could do with magnetic order. Take a chain of spins. That's centrosymmetric, then put spins down, up on that, then you lose your inversion symmetry. Now, immediately you should get frequency doubled signal when you send in a laser light beam. That background free reflects the magnetic order, even if it's antiferromagnetic, as in this case. So you don't need a magnetization, you just need order broken symmetries. And that's then the typical experiment. You send in light at some frequency omega. It's doubled in the sample, you analyze the polarization, and because symmetry is broken in different ways here, you would have different polarization components of your frequency doubled light coupling to the magnetic or electric order, so you can study them nicely at the same time, and therefore also their coupling. Here is an example. So hexagonal manganites, they contain manganese O5 cages, and then something like yttrium or some other ion here. These like to tilt in a coordinated fashion and shift this rare earth ion out of the way. That breaks inversion symmetry, so it's ferroelectric, the material in the end. But you also have manganese spin order in this triangular fashion. So you have magnetic and electric order coexisting, and indeed, you can record the ferroelectric second harmonic signal, you can record the antiferromagnetic second harmonic signal, depending on how you choose the polarization of your in and outgoing light waves and the photon energy. And then you can take pictures, ferroelectric domain structure, antiferromagnetic domain structure, side by side. So that's pretty powerful, especially if you consider techniques for imaging antiferromagnetic domains. There are not so many. Good, so let's now go through 3 examples that emphasize the 3 powerful degrees of freedom that optics has: spectral resolution, temporal resolution, spatial resolution. First, spectral resolution, or sight sensitivity in a material. We take terbium Mn2O5, complex structure, no need to really memorize all of that. The important message is you have 2 manganese sites and they form a spin spiral. Spin spiral breaks inversion symmetry and permits an electric polarization to show up on top. So it's a magnetically induced ferroelectric, a multiferroic. Okay, so then people measured the spontaneous polarization in the presence of magnetic order. Here you see the phase diagram, lots of magnetic transitions, ferroelectric order on top, so it's a multiferroic. And then they measured the very complex behavior, and also they measured that the spontaneous polarization is reversed in a magnetic field. Nice, magnetic field control of an electric polarization. And the model was, yeah, maybe there are 2 contributions to the polarization. One is field sensitive, the other one is not. But that's only a model. You cannot really, when you measure polarization, you measure polarization. You cannot say, this is from that sublattice, this is from that sublattice. But SHA can, that's the nice thing. So here we have second harmonic intensity, the frequency doubled light as function of temperature, at different photon energies and different polarizations of your light. And then you see down to a certain temperature, so here it becomes ferroelectric, and then down to a certain temperature, all curves look the same. So probably only 1 polarization contribution because everything is universal. And then you have at least 2 contributions because now each contribution couples differently to your second harmonic light wave. Therefore, you get, depending on where you probe, a different sum of these 2 contributions. Okay, and then by playing around a bit, we could even isolate. We could find a photon energy where you only see the second contribution to the polarization, not the first one. So now you can take all these curves and you can disentangle them, and then you can plot the polarization number 1. You see all the curves, they collapse on a single fit, and polarization contribution number 2. So we really separated them with this approach. And you also see there must be a third one because towards the lowest temperatures, the fits don't work anymore. So we have 3 contributions to the polarization, not 2. How is the magnetic field dependence? Here you see polarization contribution 1 and 2, they don't care. They stay the same in fields up to 7, here 5 Tesla. But contribution number 3, response. So that in total we get this picture. We have 3 contributions to the polarization, 2 that are magnetic fields relatively insensitive. There's a little shift in the ordering temperature. And the third one does this magnetic field dependence that reverses the polarization in a magnetic field. Only the third one. So, and you also see it's not really polarization reversal in the sense of switching domains. You just switch the balance or you change the balance of the 3 contributions. So you could say it's polarization reversal without actual switching. And with this technique, with this sublattice sensitive technique, we could show that. That was sight selectivity or spectral selectivity. Now let's look at time resolution. These experiments are always done with lasers, mostly. Short pulse lasers, femtoseconds, so you can really, like in the stroboscopic fashion, you can image processes down to femtosecond resolution. And here we have an example, europium oxide, a ferromagnetic semiconductor, which orders at a surprisingly high temperature for a rare earth material at 70 Kelvin. And if you put in a little bit of gadolinium, you even reach like 130. The thing is, when you replace europium by gadolinium, you get an extra electron that goes into the conduction band and connects the 4F shells better. So the magnetic ordering temperature goes up. And here we asked ourselves, maybe we can populate this 5D band also by pumping electrons there with a light beam. So it's a kind of photo-induced strengthening of the exchange. So yeah, that was the question if that is possible. So this is the experiment we built, a strong pump pulse that populates this conduction band, and a second probe pulse that probes the magnetization by second harmonic generation, again via this symmetry breaking aspect. And indeed, what you see is that when you pump your sample optically with a strong pulse, the second harmonic signal goes up by 20–30%, so really a lot. That means your magnetic order gets 30% stronger because you probably because you populated this conduction band. And that contributes to a better exchange between the 4f ions. In the end, then, you fall below the original second harmonic intensity, but that's mere heating. So this is also interesting. This enhancement hits before the high temperature hits. But in the end, the high temperature wins. Okay, we can do this then with the different gadolinium doping concentrations. Here we have the curve that we just saw. And then for different content, gadolinium content, you get more. So you see at some like 0.25% gadolinium doping, you get an incredible enhancement of your the magnetic order. And that lasts very long. It's not even beaten by this heating effect in the end. But then if you dope even harder, then at some point, it's not a photo-induced enhancement of your magnetic exchange, of your magnetic stability, but now it's a photo-induced attenuation. So apparently you can control, with light you can enhance or attenuate your magnetic order. And then we have this very nice collaboration with Hans Kroher. I always tell my group, if you have a problem, ask Hans, he knows everything. He can explain everything. Probably faints now up there. And so then two mechanisms that we identified. One is indeed you populate the conduction band, and that strengthens the magnetic order. But it wouldn't attenuate it. The attenuation is because you populate this conduction band, you also work on the RKKY interaction. It gets less ferromagnetic, so in the end, if you have a lot of population up here, your exchange interaction simply weakens in terms of the RKKY exchange integral. And this is a balance so that you can nicely play here for enhanced or attenuated magnetic order. Good, that was the time aspect. Now, spatial resolution. You can see domains. That's super exciting. Therefore, it comes last. That is a very old picture. So basically, for my PhD thesis even, that shows that you can image antiferromagnetic domains in chromium oxide. And these are spin reversal domains, or 180-degree domains. So there's nothing secondary like magnetostriction that you can use for foreseeing this order. But with this second harmonic imaging approach, you need a minute, and then you get a few micrometers resolution. The only other picture that was taken of antiferromagnetic 180-degree domains, that was polarized neutron scanning experiments, 24 hours, 100 micrometers resolution. So this is really, in that sense, unbeatable as a complementary technique to image magnetic order. Then multiferroics happened, so with this coexistence of magnetic and electric order, and very much more complicated structures were looked at. So for example, here we have manganese germanate, and it's super complicated. Don't even try to understand the structure. So you have different manganese sites, and you have spins forming cones, conical spirals, and a lot of stuff. But in the end, that leads to a spontaneous magnetization parallel to a spontaneous electric polarization. And they can be oriented parallel or anti-parallel. That's exactly what you want from a multiferroic. But if you tune it to that degree, so polarization and magnetization and parallel and switchable, then you need a lot of order parameters to get that. I mean, it has to be complicated in order to fulfill all these functionalities. So in fact, then you have 2 commensurate and 4 incommensurate order parameters that make this work. And then the question is, if you have so many building blocks, so many order parameters, you can possibly do other things than just magnetoelectric switching. Like tangram, you can assemble 7 pieces into many different shapes. And we wondered, are there any such functionalities that go beyond the mere magnetoelectric coupling? And here you see such a functionality. So we imaged a ferroelectric domain structure. by second harmonic generation. We apply a magnetic field to it, and the electric domain structure changes. And you would say it completely shifts domains around. But when you look at the first and the last picture, you see the magnetic field goes from one domain structure to another. It looks the same. It's just that in every spot, the polarization is reversed. So it's a kind of domain inversion. Domains stay, but polarization is reversed everywhere. Nice functionality. It's a kind of holistic knot operation. How does it work? You can understand it because you can write down a free energy that couples to the polarization, to the magnetization induced by, controlled by your magnetic field, and some coupling constant. And now if you change the sign of the magnetization with your magnetic field, that's what we do here. Polarization has to reverse as well to keep this free energy at minimum. So polarization compensates the sign change of the magnetic field-induced magnetization. That's why everywhere P changes sign, and you keep the domain structure that is on top. So domain inversion, a nice functionality that is more than just magnetoelectric coupling. Another example, dysprosium terbium ferrite. So here, the dysprosium and so this rare earth side and the iron side together create an electric polarization through magnetostrictive effects. So you have a polarization, a magnetization, and so polarization created by the magnetization of the iron lattice and the antiferromagnetic order in the dysprosium terbium lattice. So three order parameter kind of equation. Free energy is given by the product of all three of them. So when you now start switching, then if you reverse if you reverse M, P compensates for that. And if you reverse P, M compensates for that if you apply your electric polling pulse fast. There are more complicated scenarios that I'm not discussing now. The message is M changes with P, P changes with M. Okay, that leads to the following nice experiment. You start with a magnetic domain configuration on a single domain ferroelectric background. Now you apply a magnetic field and you make your structure magnetically single domain. Polarization has to compensate, so the domain pattern jumps from magnetic space to electric space. And then you apply an electric field pulse that makes your sample ferroelectrically single domain again. Magnetization compensates, the domain pattern jumps back to magnetization space. So we called that jokingly teleportation of domains from magnetic to electric space because you don't duplicate. You destroy here and you recreate there. That's exactly what teleportation is about. And even submitted that. Maybe it's some corona effect. We found it funny. And then the editors and 4 referees, they took out the big stick. No science fiction, guys. So, but they liked the work. So in the end, we published it as magnetoelectric transfer of a domain pattern. Okay. Very last example for the final 5 minutes. That is a little bit out of these 3 degrees of freedom. It's basically something useful even. I always said I'm not doing anything useful, but in the end we did something useful. So we wondered, so when you grow a thin film, a ferroic thin film, how do you see it's really getting ferroic as you want that? You have electron diffraction that tells you that you are neatly building atomic layer on atomic layer when you grow a thin film. But you cannot see why what you grow the film for, namely, does it properly get ferroelectric or magnetic? So then we said, okay, let's just not only send an electron, but also light beam into our chamber that can probe this. So now we can see a sample growing. We send light onto the target, and we see the very moment when it gets ferroelectric or magnetically ordered or whatever. Yeah, that is actually then what this grant was awarded for, and in the end we even got some money to build a prototype that in principle now could be sold sometime in the future along with READ as in-situ detection technique for thin film growth. So here's an example of what I mean. So when you wanted to grow a thin film and make it properly ferroelectric, so in the past you would grow different films at different thickness. You take them out of the chamber, you characterize them ferroelectrically, and then you need 4 data points, 4 days to basically have 4 data points. We do it during the growth. So it takes us like 20 minutes, we collect 100 data points, and then we see here there's a second harmonic signal emerging. So when you grow bismuth ferrite on some metallic buffer layer onto a substrate, 4 unit cells, that's where the ferroelectricity starts. And it's really so easy in this way. And that's just tracking the growth. Now you can see things happening during your growth that once the growth is completed, you do not see anymore. Example is here. So here we have lead titanate grown on strontium titanate on a dysprosium scandate. And if you grow on strontium titanate, the second harmonic signal just grows. That means your film gets ferroelectric, it gets thicker, so more signal. But when you grow it on dysprosium scandate, which is a little bit more strained, also your second harmonic signal grows. So that means net polarization grows. Then it decreases, then it grows again. So that means sometime during this growth, it does not grow in a single domain, so out of plane polarized fashion, but suddenly that gets unstable and the polarization collapses. It now forms regions that are in plane polarized. So they are lost for your signal. And you even have not just these growing anew. Some of originally out of plane polarized regions, they flip. And that's why the signal goes down until that has stabilized, and then it just gets thicker again. So these things you can see by in situ second harmonic generation as a new in situ sample characterization technique. And with that, I'm coming to the end. So I hope that I have explained or shown to you that first, aside from ferromagnetism, there are many, many different types of ferroic order that nature knows, bizarre things that are even proposed to be ferroic, but that await verification. The common basis is symmetry breaking that we need or that we use for doing our experiments. We don't care about the origin. We just look at the symmetry, and that makes things simple. Because now electric, magnetic, you need different probing techniques usually, but both break symmetry, so both can be seen by the same technique here. I explained to you how we use the optical degrees of freedom to get interesting information about out of ferroic and multiferroic materials. Nonlinear optics is particularly useful for studying multiferroics. And before I finish, I think I have 1 minute left, so there are no questions to these prize talks, so I can use the time for advertising. So as you see, there is this book that comes out in July and where you can read everything about this. And we lock the door, so only people who buy a book can leave the room. And the good thing is I have discount vouchers. So come here, pick these up. Thank you.
Thank you very much, Manfred. And I guess for each book you sell, you get a beer, or you have to pay a beer. So just go to Manfred and ask for the beer. Okay, there are no questions. You have already heard it. We will continue here soon with the Festsitzung after some change here in the room. And with that, I would like to thank you, Manfred, very much, and you for listening. And with this, I close the session.
Thank you.